One thing we can do when designing an algorithm is to make some assumptions about the properties of our data that may or may not be true right off with the data that we're handed, but that allow us to think through a process. If those assumptions were true, then what could we do from there? And then we can sort of work backwards to think about how could we get those properties to be true about our data. And perhaps if we can do that in a cheap way, then we can get whatever good performance we may have designed for data that has those properties. For example, rather than thinking about sorting a whole set of all of our data that may be in any particular order, we can think about the goal of combining two sets of already sorted data into a single set that's fully sorted. For example, if I have piles of exams that came from two different sections of the same course, and I know that they're sorted within their own section, but I want them to be one sorted pile of all students' exams, then what's the simplest way to combine them into a single sorted pile? So the stack starting with C is its own pile, and the stack starting with A is its own pile. And what could I do to get those into a single sorted pile? And it may be helpful to think about how many steps or how many operations it might take to combine those into a single sorted pile while you're at it. So pause the video and think about what the simplest way, the simplest procedure would be for combining these two piles of letters, abbreviations of names, whatever, into a single sorted pile. One thing that you might notice, if you're looking at the data and thinking of it as piles of physical objects, is that the minimum value from both piles will always be the top of one pile or the top of the other pile. So in this case, for instance, I can see that A is lower than C. I know that C is the lowest value in the left pile, and I know that A is the lowest value in the right pile. And so therefore, I know that A is the minimum value from all of the values that are present. So A will go into my pile first. Then, since A was removed from this pile, B would be the top, and I only need to compare B to C. So I see that B is lower, and therefore B will go into my final pile. I then can compare F and C, and I'll see that C is the lower one, so C goes into my final pile and is removed from its own pile. Between F and D, D is lower, and so D will go into my final pile and be removed from its own. Between E and F, E is lower, and so E will go into my final pile and be removed from the other one. And then I have between F and G, so F will get moved over to the final pile. Then it's between G and H, and G is lower, so G will get moved over. Now I see that the left pile is empty, and I know anything remaining in the right pile can just be copied over. So in this case, H kind of comes over for free, and we get the full sorted pile of all of those values. Now, if we think about the performance of doing this combination, it's actually really good because we didn't have to dig down into lower values. We didn't have to step through every value to find what should be our next choice, like finding a minimum or something like that in unsorted data. But it did rely on the property that these two lists, these two piles, had to both already be sorted. When they were already sorted, we got from 8 values, we got the sorted resulting list pile in only 7 comparisons. We got H kind of for free there. So for N items between the two piles, we might get the full list in close to N values, N minus 1, maybe even less if we're really lucky. But, of course, we don't get data that's already in sorted arrays or partial arrays or things like this. What we could do, however, is we could look at real data and we could think about what we could do to get the features that we want from it. So if I take this data here, that's all the same values, A through H, and it's not sorted at all, what can I do to try to get it to behave in a way that gives us this nice about n comparisons or n minus 1 comparisons sort of behavior of combining piles? Well, if we think about that there do exist some lists, some arrays that are always sorted. For instance, arrays of single values are always sorted. The item B on its own is always sorted because it has nothing to be compared with. C on its own is always sorted, and so on. If I treat every item as its own array, then I have 8 sorted arrays here. And then I can be combining them. I can be combining the B and C arrays to get B and C as its own small array of 2. I can combine A and E using the same algorithm and get the A and E array. I can combine H and G. And I can combine the D and F that are left here at the end. And now I have some partial sorted arrays that are even more than one item. And those were obtained pretty quickly by just looking at the tops of these single item arrays and finding the ones that that come first. Then I'm combining pairs. Combine the B and C and the A and E, where I would take the A from one list and it would be removed. I would take the B, I would take the C, and then I would take the E. And that gives us a list of 4, an array of 4 items, and the other one will give us an array of 4 items as well by combining this 2 and this 2. And we can see that this starts to give us good combined lists that will then merge into a whole list. D, F, G, H. And in fact, we're even really close to having the array sorted at this point. We have a chunk of 4 that are relatively sorted to each other and another chunk of 4 that are relatively assorted to each other. And then I'm picking the tops from each. So I would see between the tops here, A is higher or is earlier than D. So I pick A. Same for B compared to D. Same for C compared to D. And then the first time I'm picking from the other array is the D after C. Then I see between E and F that E is the earlier one. So E will get put in there. And then I see that my left one is completely empty. And so I can just take the F, G, and H and copy them up. So we did this at that level with pretty few comparisons. Now I have to do multiple levels of combining these, and I have to somehow sort of conceptually break them down to single items, which then become pairs, and then become 4s, and then become 8s. But we were able to apply that procedure of combining sorted lists at every level here. You may, if you're starting to get a feel for recursive things, see that there's kind of a pattern of a recursive sort of thing in here where we have a base case of a single item, and then we come back up that recursive stack and start combining things. And once we do that, when we get back all the way to the top, we have a fully sorted array. So this will give us the basis for the merge sort algorithm, which you're going to look at today, at least in part, and we won't have to think too heavily about the performance or kind of the implementation details, but I want you to start to think about this idea of merging sorted arrays and how if you go with that assumption that you have sorted arrays, then you can build a sorting algorithm based on that even can handle completely unsorted data because you work with this convenient definition that single arrays are always already a sorted array. And so take a look at those, start to think about how you could build an algorithm like this and how this kind of recursive approach might change the game plan and change the behavior of the algorithm that we come away with.